on the ball. Now this trips up a lot of people. So I always love this number. Go ahead.
Could you just like move it up a little bit?
So we're going to do a free body diagram, which is simply what are all the forces on the body? Forces on a projectile moving from left to right. What are all the forces? And I always start with the easy force. The force that's on everybody is the force. Forces on you, forces on me, forces on the table, forces on the chair, forces on this building. What is that? And which way does gravity always point? So right down, it's got an arrow. So that's easy. Good, I'm recording. Just let me be sure that I'm recording. And yeah, let's do the easy force. That goes straight down. You can call it the F sub G or the force of gravity or the weight. The weight force. So you never can go wrong putting the weight force on the free body diagram or force. You're going to learn soon that the weight force is the force of gravity. That's what weight is. What we always call weight is the force of gravity. Now this ball is hit really hard. It's going super fast, and it's got a little what force opposing its motion. Little tiny. Yeah. So friction is going to be a little. Let's put a little tiny friction force. It opposes the motion. We're going to be learning about that soon. Sorry for making. Let me erase. That's terrible. That is really bad. So let's make a little tiny friction force opposing the motion. Call it friction. So the next question is always done. Yes. But you know what I forgot to do? I'm going to get back to you. I'm owed a lab from, who owes me a lab here? Miss Cruz and Miss Wagner. Can I have your labs? Please bring them up. It's the resultants and equilibriums lab. Oh, maybe I didn't check it out. Let's see. What's your number?
8.
You're 8? Maybe I got it and didn't check it out. No, there is no 8. Maybe it's back here. You sure? Come up here and see if you can find this file. Just put your lab, the swag in the front. I think you're in the back. Just put it underneath right over here. Yeah. Samantha, do you want to take a look at this pile? Maybe you're thinking of I might be thinking of a different lab. Just put it underneath. It's just the back. No, don't put both of them because this goes and I'll take it. Okay. This is the lab I want. I think you owe me 2 labs. Yeah, I think you gave me. Yeah. So look for that one. All right, girls. Sorry about that. Now, so is there another force or are we done? What do you say? Who thinks they know? Yeah. Well, I'm so glad you brought that up, and I don't think I did a good job when I talked about normal forces. Normal forces are only applied, only rigid forces apply normal forces. Let's add that down. Right? Only rigid, so that's my fault. Let's write only rigid forces apply normal forces. Like the chair is applied, is normal force, on you.
On top of it?
Yeah, something on top of something. Good. So let's write only rigid surfaces apply normal force, like the chair or the floor. Yeah, the chair. The chair is applied.
Rigid, would
Yeah.
that like not be circular?
No, it could be any shape. Like you could be sitting on a ball, and that would be applying normal force. Something that's rigid and unyielding, like the floor applies a normal and the chair.
So like not moving?
Yeah, air doesn't apply normals. Yeah.
Can you have 2 normal forces? If you're sitting on a wall, the wall is.
Yeah, you could have 2. I could be on a chair, leaning on a wall. Good. That's advanced stuff. I could have 2 normal forces on me now. So let's write air does not apply normal force. Air does not. Thank you for bringing up normal forces. I don't think I did a good enough job of saying that only rigid surface, like a chair or a floor, or a wall. Terrific. Yeah, if it gets a wall, that would be a normal force as well. There is no normal force because the air doesn't apply normal force. Are you ready? You might be surprised. We are done. Now, some people would say that's ridiculous. Isn't the back force on the ball? I remember when I was reading studies of students' misconceptions, they think that the back force is still on the ball. No, once the ball loses contact with the back no longer applies the force. And you know what? When I was yeah, oh, great question. And what a student would say is, no, the back force is on the ball because how else is it moving forward? And here's the thing. You don't, once that object is set in motion, it doesn't need a force to stay in motion. The Bats, let's write this down. Bats force is not on ball. Bats force is not on ball. And she said the perfect thing. She said, well, why is it moving forward? Right, continues to move forward because it's an object in motion. Continues to move forward because it's an object in motion. The Bats force is not on the ball. Continues to move forward because it's simply an object in motion. Now, don't feel bad at thinking that there's a force that makes it continue to move because one of the greatest geniuses of all time, Aristotle got this wrong too. He thought there must be a force that keeps moving the ball forward. He was wrong, like Aristotle was wrong about practically everything. Unfortunately, what happened is Aristotle was right about so many different things. When you go to college, you probably read Aristotelian ethics. He was a great philosopher. He was a great biology. He made a lot of contributions to biology. But for some reason, he got practically everything wrong about physics. And because he was so brilliant, people said, well, he was brilliant in this field, he was brilliant in this field. People tended to think that everything he said in physics was true. And it really set physics back a long time. Because for you to disagree with Aristotle, you better have some good, well, the community would say, who are you to say that Aristotle was wrong? You know what, every great genius is imperfect in different fields. You know, they get things wrong. Always remember that as you go out into the world and you are surrounded by smart people, as you will be, that they are smart in their field, and oftentimes when it's not their field, there's a tendency for people to think everything they say is right. It's called the halo effect. Is anything called the halo effect? It's something you'll see as you get older. The halo effect is if someone is brilliant in a certain field, there's a tendency for people to think that everything he or she thinks is right. And we have to fight against that. Now, I would hesitate if, all of a sudden, Bill Gates is talking about computers. I might shut up. I don't know. He probably knows a lot more, but when he's talking about other areas, I may still be quiet and think. But I may say, well, maybe this is a halo effect. Maybe he's out of his field of expertise, and while he's brilliant and a genius, maybe he's wrong about that. So I want you to think that as you get older, be surrounded by other smart people. It's called the halo effect. So you just learned an important lesson of life, that just because someone is super brilliant doesn't mean they ever get something wrong. And Aristotle, I always say that Aristotle ruined physics. I don't know if it was Aristotle, maybe everybody else who was so hesitant to question what he said, maybe they're the ones that were wrong, who imbibed this halo effect of saying, could Aristotle be wrong? And like I said, he was wrong about almost everything he said about physics. And did it set back physics? No, we set back physics because we stopped questioning it. But this guy did. His name is Galileo, and he questioned a lot of things that Aristotle said. What he proposes, an object in motion doesn't require a force to stay in motion. An object in motion does not require a force to stay in motion. And now, could you write end of test 1 first quarter? Because we just ended the material. That will be in test 1 first quarter. So what does it include? Forces, and forces in motion. Everything after the last test of the last quarter. And so it starts with forces. So you have to do adding forces. Everything on the quiz will be on the test, and all the 3 laws of motion. But now, could you get out the gravity notes and write beginning of test? Could you write beginning of test 2, second quarter? gravity notes, beginning of step 2, second quarter. I should take a picture of the moon. Oh, no. This guy right here. This guy right over here. This guy right here. Looks like this. Looks like this got a single sheet of paper. Could you write the beginning of step 2? Beginning of step 2, you need that?
Yeah.
Could you go get, who else needs to raise your hand? If Claire's gonna give it to you, and you keep your hands up. Okay. So it looks like this, a single sheet of paper. So who is drawing the arrow? I think you are, if you don't question someone, if you disagree with someone that's brilliant, remember to question them. So keep your hands up. Terry, did you find them?
Yes.
She's got them now. Gravity, who taught us almost everything about gravity? Who was that person? That was everybody attributes, when you think of gravity, you think of Isaac Newton. Sure. Of course, he didn't teach us everything about gravity, but for a long time, everything we knew about gravity came from Isaac Newton. It is universal law of gravity. Put that on the top. The universal law of gravity. Now you know what universal means, right? This law was literally a universal law. So right on the top, the universal, right on the top of margin, up at the way top in the margin, the universal law of gravity. Now, I just want to tell you that, let's look at that word universal. When he said universal, he literally meant this law is universal. What does that even mean, that it's a universal law? What does it mean to be universal? Universal.
It applies to the entire universe.
Yeah, now you're so modern, you think, okay, big deal. It's a universal law. This blew people's minds. And I want you to prep your modern people, but when Newton proposed this law of gravity, it was a law that was true here on Earth and out there in the heavens. Why did that blow people away at the time? Because you're modern people, and when you look up at the heavens, and I tell you that all the elements that we have here are out there, you're not impressed. You don't say, wow. But if you listen to 1600, you say, wow. Newton found a law that was true here, that worked here, and worked out there. Whoa. Even people who weren't physicists, were just philosophers or thinkers, their minds were blown away. That the rules of the rules down here applied out there, it was really a game changer. And when they found elements here that were there, nobody was shocked or surprised, because Newton opened the door to say, well, maybe this universe is where we live. Well, maybe it's governed by a single set of laws. There's not a single set of laws here, there's a single set of laws out there, which was what people believed at the time. They were earthly laws and heavenly laws. Yeah. So it was Newton who changed that. It applied even out to the universe. And maybe Newton started to think about this law as he watched the moon when I let the dog out at night. I always find where the moon is. I'm waiting for the dog to do his thing back. And I always look up at the moon. I look up at the stars, and I noticed that the moon is always in a different position. And you watch it, it'll curve across the sky. If it's a full moon, it'll be in the east, and then it takes different positions, and you could follow that path across the sky. Well, Newton looked at it and said, well, maybe it's just a big old rock. Maybe the reason why the moon curves across the sky is the reason why when I throw a rock across a field, it curves. It's just a big rock. Maybe it has the same force on a rock as on the moon, which is not true. Doesn't blow you away, but it blew people away. That the moon is simply a rock with the right speed. Not too what? Not too fast. Well, if the moon had in the beginning too fast of a speed, what would happen? If its initial speed was too fast, what would happen to the moon? What would happen to this rock? It would escape the Earth's gravity and fly away. If it was too slow, this proved that a lot of the stuff that spun off the universe was too slow, it would curve and crash. So the moon had the right speed, not too fast, curve up, not too slow, smash in, and be just one more crater, one more large thing that popped the Earth. And so it's one thing to propose that, it probably wasn't that, a lot of agreement, but he did the physics on it. Yeah, he worked out the physics in pages and pages, and he proved that the moon was just a, yeah.
So was it like, asteroid or something?
Now, we're not quite sure. A lot of people believe that when the early Earth was molten and liquid, and a piece of the Earth spun off, and it got caught in that gravitational field. Or some people think of the impact theory. Maybe there's just something that came in here, smashed in, and tore out a piece of the Earth and got caught in our gravity. I don't think we know the origins of the moon, but I think the impact theory is the most prevalent theory. I'll look into it again.
Oh, is that why people think like the Earth is on its own?
Yeah, did that impact tilt the Earth? I don't know. See, that's what now it's Earth science, and I'm a little shaky on the Earth science. But the point is, it had the right speed, not too fast. Curves away and escapes the Earth's gravity, not too slow, smashes into the Earth and it's gone. So Newton did the physics and proved, yeah, the moon is just a big old rock that has what's called gravity on it, that invisible force of gravity. He said that gravity is the mutual, now you F sub G, gravity, put it underneath the universe, still underneath the margin. Gravity is the mutual force of attraction. Gravity is always attraction.
Are we ready to hear?
You know, just still going, I think you want to be above that still. Gravity is the mutual force of attraction. It's always an attractive force between any two objects in the universe. Any two objects have gravitational force. Is there a gravitational force between me and this staple? Yeah, it's like incredibly tiny. This staple and I have a gravitational force. If I calculate it, it'd be ridiculously small. Besides, something else is pulling on this much greater than I am. You know what else is pulling on this staple besides me? That's pulling it way stronger. What is pulling on this stapler? What's applying much greater gravitational force? The Earth, like a gazillion times more than the force that I observe. But technically, he said it's the force between the Earth and the Sun, and the Earth and the Moon. They have a significant gravitational force. The Moon is responsible for the tides, you know that, right? The Moon lifts our water up and brings it down. And we apply it. Now, let's talk about that first word, mutual. What a good word. Like if I said the feeling is mutual, you know, when someone says to you the feeling is mutual, what do they mean? Yeah. The same, you're like, I hate you. You say, well, the feeling is mutual. I hate you too. Now, mutual means it's equal. What law of Newton would tell us that the Earth pulls on me and the Earth pulls down on me, but do I apply a force to the Earth? Yes. And it's mutual. Which law are we talking? Think about that. It's the third law. One of Newton's great three laws that when object A, B, exerts force on object B, Earth, object Earth exerts force on me. If I exert a force on Earth, the Earth exerts a force on me. How do those two forces compare? They are what? Equal and opposite. Now you might say that's ridiculous. Look, it's very clear that the Earth exerts a force on me. I mean, look what it does when I jump up. It pulls me down. I exert a force on the Earth. The Earth doesn't jump up to meet me. Well, what does the Earth have a whole lot more of than I do? It has a whole lot more mass and inertia. So I exert a very tiny force on the Earth. When I change the Earth, does the Earth jump up to me? No, it has a gazillion times more inertia and a gazillion times more mass. That's like saying, you know, I walk and I get into a flea. Did it slow me down? Oh, come on. I don't know, I guess I could calculate what the flea slowed me down, but it's a flea. Look at its mass and its inertia. It didn't slow me down much, or its air molecules as they walk. Did that slow me down? No, they have too little of inertia, so we have a big impact on the flea, but does the fleet change my motion? Really slightly small degree. Now here is the equation for gravity. Could you put that thing in the blank? Force of gravity equals F sub G. Force of gravity, F sub G, depends upon all these things. I wonder what these two things are. I bet you know. M1 and M2, what does M stand for? Obviously. Mass. The mass of both bodies, this is a constant, and R. Let's see what R is. G is a gravitational constant that's on your reference table, and you don't have to memorize it. It's on your reference table. It's on page 1. Did you get all that down? That's a really small number, that G. It's the first thing on your reference table. That's it. All right. M1 and M2 are the two masses that are involved in the attraction. Now let's see if you can listen. It's better, very. Compare the force of yellow on green with green on yellow. Because there's a force between them. Good, she's good. Equal but opposite. Now a lot of people would think the green exerts the biggest force on. I'm sorry, the yellow exerts the biggest force on the green because it's bigger. Nope. Newton says it's equal but opposite. Equal but opposite. So that's what. Now R is the distance between the center of masses. Could you write down this? This is R. I don't know why they called it R. I think it's between their radial centers. Maybe that's why they didn't call it D, they called it R. The distance between the radial centers. Do you know if you went to the highest mountain in the world, you took your scale, you know the scale you use in your bathroom? You took your scale, you know, you went trekked up to the top of the highest mountain, put the scale down, stepped on it, and you would weigh different or the same. You weigh a little, yeah, you weigh different. The top of the highest mountain. Now, not much different, but would you weigh less or would you weigh more? We can transport you in a rocket ship to the highest mountain. You land, we put down a scale, I look down, oh, I weigh different. I weigh a little less because I'm a little farther from the center. Would it be like an ounce less? Like an ounce less. Maybe a third of an ounce less because even on the highest mountain, you're not that far different. Yeah, tiny. Because you're a little further away. Now, let's do relationships because we always do relationships. So, right? We always do relationships. What's the relationship between force of gravity? It's proportional to the product of the two masses. Let's see how that works. So I've got two bodies and they're separated by one body is X and one body is Y. But then it's got a force of gravity 100. If I could snap my force and double one of the masses, but leave the other one just the way it is. Double one. Now, do we have more gravity or less? Does that double one's mass? More gravity, right? Now the question is how much more? If it's not 100, but more, what's the new gravity? What's the new gravity? It's not 100, it's more. What is it actually? Because I've doubled. Nobody knows? It's, what do you say, Miss Wagner? What do you think? Oh, you're good. 200. She knew that. She saw a direct relationship. Let me show you what I think she was thinking. Could you write this down? F is G. It's really quite simple. Look, you doubled one of them. If you double creates double, right? They're both on top. So it's not 100, but it's 200. Now we'll get a little tougher. Ready? How about if you doubled one and tripled the other one? Now it wouldn't be 100 anymore. It would be greater, of course, because both masses are bigger. Let's see how good you are now. It would be what? Well, it's actually quite simple. Watch. Watch this. I look at the equation again. That's in my reference table. Oh, you're doubling this and you're tripling that. Double and tripling. Look. it's not going to be 100 anymore. Who knows? Now somebody knows. What do you say? Samantha knows. 600. What did she do? She simply 2 times 3. If I'm changing 1 by 2, changing 1 by 3, 2 times 3 is 6. I plug the changes into my equation, and it goes up by 6. Good for you. Now, at this point, you should get it. What if you, Noel, what if you only quadrupled one of the masses, but keep this one the same, but quadrupled y? What would be the new number? Not 100. I just quadrupled y. It's not 100 now, it's very good. Because it's direct, right? Now, this one's a good one. What if you half x and you tripled y? Half times triple. This numeric knows this one.
Maybe.
I knew she knew. Because I hope you see that you did 3 times a half, which is 1.5 times 100. Pretty good, right? So Regis likes that if I change this and this, what happens to that? And you plug the change in the equation like it was a number. Plug the change. This one's tough, so I'm going to break it. What did she do? In her head, she said, well, I just learned the equation. It looks like that. And multiply this by a half and tripling this. So triple times a half is 3 halves of 1.5. And so the change is 1.5 here. And this changes by 1.5 as well. Do you see 100? Now it's 150. That's tough, right? Good for you for getting that. She did it right in her head. FG is inversely proportional to the square of distance. Now here's a new relationship that you never saw. Inverse square. It's your fourth and last relationship. Inverse square. Your fourth and last relationship. And it looks like the inverse, doesn't it? Let's write that down. Looks like the inverse. Looks just like regular old inverse, but goes to infinity and 0 quicker. It goes to infinity and 0 quicker than inverse does. Well, the Regents want to know that you know that now. They just want you to know that both have similar shapes. Looks like the inverse, but goes to infinity and 0 quicker. Cool?
Wait, do we need to know what you wrote down?
No. You'll never have to distinguish between the inverse. Everybody thinks I have to distinguish between the inverse and the inverse square. Will they ever give me both those traces? No. Just know the inverse square goes to infinity and 0 quicker. Now, let's see if you can use the inverse square. Ready? Let's all rewrite the equation just as practice, even though it's on the reference table. This is an inverse square. See, top and bottom is inverse, and the R is squared. Inverse square. So what if I double the distance between the moon and the earth? Double the R, double the distance. Would the gravity be weaker or stronger if I double the distance? Gravity would be weaker, of course. What fraction weaker would it be? Very good. Double, it would be close, not a half, but because it's an inverse square. Quarter. What did she do, Kendra do? She not only inverted it, but she squared it. And that's because the R is squared, right? Inverse square. Let's see if you can follow this. Ready? How about you triple? Oh, now it's even weaker. Triple. If 2 was 1/4, Samantha Cruz, what would be 3? 2 is 1/4 of the force. 3 would be 1, not 1/6. It would be 1/9 because you square it again. You square it and flip it.
So this means that if you multiply the R by 3, then you multiply that S by.
Good. Yeah, if you multiply the R by 3, let's write that down. What does this even mean? What am I talking about? If you multiply, let's write what you said, R by 3, force would be 1/9. That's great. It would get weaker. It would be 1/9 of what it used to be. 3, 2 gives you 1/4. 3 gives you 1/9. 4 gives you, let's see, is that the next one? Is it 4 the next one? Let's see. Oh, 4 gives you how much weaker? 1/16. All you have to do is square it and flip it. Inverse square. Flip, inverse, square, 1/16. Now, here's an interesting one. Did you add this one to you? I'm not sure it's on your chart. What if you make them closer? 1/9 the original distance. Now what do you do? What do you do? What do you say, Carrie? Oh, good for you. Now you didn't take much time at all. 9. She flipped it and she squared it. Good. So you see how the Regents loves that question about if you change one thing, how it would have happened over here. And let's go with Orla. What do you say, Orla? Could you do 1/4? Absolutely. Could you add that to the chart, girls? Because sometimes they make these charts too small. So add to the chart. Okay, you get the concept here? That's the inverse square, the last relationship that you need to know. Now is this on your sheet? No? I'll tell you what, could you draw this? It'll be the last thing we do. There are 2 planets. Could you draw this? There's on the Regents one here. Find a place to draw this. Where can we draw it? Let's see. How about on the bottom right? Could you draw that? You've got a planet that has 2 satellites around it. One's close, one's far away. As you draw, who's got the strongest gravity force on it? Is it A or B? That's an obvious question, isn't it? Who's got the greater force of gravity on it? Is it A or B? A or B? One's got a stronger force on it. A or B? What do you think, Lauren? I'm going to give you softball questions. Who's got the stronger force? Is it A or B? Stronger force on gravity. You don't have to tell me how much stronger, but who's pulled on? Who's receiving a from planet A? Who's feeling a stronger force on planet A? Is it A or B? What do you think? Hey, it's closer, right? But that's actually not the question. Let's see the force. Let's go over here to satellite A, and we're told that it's 160,000 newtons force on it. That's a really big force. Then they say, what's the force? Let's call that F sub G. Now, what's the force of gravity on one that's twice the distance? Oh, this was a tough question, wasn't it? Twice the distance. Its force is not 160, it's less. It's a fraction less. Who knows?
First women and sophomores may leave.
Good. Oh, did you hear that? Good, good. Say it again. Yeah, so it's not 160. Terrific. Good job. Good job. Nice. Last question. What's the halo effect?